In a dim room before electric light, a glass jar sits quietly on a table. It does not glow. It does not hum. It gives no warning to the eye. Someone has turned a machine, rubbed glass, built up a charge, and touched metal to the jar. Now the room waits. A hand reaches forward, and in the next instant, the body jerks back. A spark has crossed a gap, and the invisible has entered the nerves. For centuries, electricity came to human beings in moments like this. It clung to amber after rubbing. It flashed across storm clouds. It stunned the hand, twitched the muscle, bent the compass needle, and passed through wires before anyone could say clearly what it was. People could feel it long before they could explain it. They could make it appear in small ways, store it imperfectly, guide it dangerously, and misunderstand it again and again. The history of electricity is not the story of one clean discovery. It is the story of many wrong ideas becoming better instruments. A jar seemed to hold a mysterious electrical fluid. A frog's leg seemed to reveal the secret power of life. A wire beside a compass seemed like a minor disturbance until it opened a path into electromagnetism. A moving magnet inside a coil produced only a brief flicker at first, but that flicker would one day become the principle behind generators. Electricity did not wait for human beings to understand it before it changed their world. It was already in the storm, in the body, in matter, in magnetism, in light. The human task was not to invent electricity, but to learn how to notice its patterns, test its behavior, survive its dangers, correct the errors, and slowly build a map of a force no eye could see directly. Tonight we follow that slow map making from amber and sparks to jars, lightning frog legs, batteries, magnets, fields, waves, and the glow of the modern city. How did human beings come to understand a force they could not see, and how many wrong ideas had to fail before the electric world could finally begin? Long before electricity had a name, it appeared as a small disturbance in ordinary things. A piece of amber rubbed with cloth or fur could begin to pull bits of straw dust or dry leaves toward itself. A strange fish taken from the water could numb the hand that touched it. A dark lodestone could draw iron close with a quiet steadiness. Far above all of this, lightning split the sky with a brightness too sudden for the mind to hold. To ancient observers, these signs did not yet belong together. Amber was one curiosity. Lightning was another. The shock of a fish belonged to the sea. A magnet belonged to stone iron and navigation. Each phenomenon had its own place in experience, and no single idea tied them into one story. The world had not yet been wired together in thought. That is where the story of electricity begins, not with a lamp, a motor, a battery, or a power station, but with scattered encounters. Human beings noticed that matter could behave strangely when rubbed, touched, struck, or brought near another object. Something could pull without a rope. Something could stun without a wound. Something could flash without ordinary fire. But noticing is not understanding, and for a long time, these phenomena lived in separate chambers of the human imagination. A storm belonged to the heavens. A fish that numbed the hand belonged to the mystery of living creatures. A magnet belonged to the strange sympathy between stone and metal. Amber belonged to little demonstrations of attraction after friction. The pieces were real, but the pattern between them was not yet visible. The Greek word for amber electron would one day give electricity its name, but the word came long before the modern concept. To see amber attract light objects was not to understand charge. To feel a shock was not to know what had passed through the body. To watch lightning was not to know that the sky and the laboratory would someday be joined by the same science. Nature often shows its behavior long before human beings have the language to describe it. A person can see a spark and still not know what a spark is. A hand can recoil from a shock and still not know what has crossed the skin. A sailor can trust a magnetic compass and still not know why the needle turns. Practical familiarity may arrive centuries before explanation, and for a long time, that was how electricity lived in human life. It was useful, sometimes frightening, sometimes entertaining, sometimes, but not unified. Lightning was the grandest sign. Unlike amber or lodestone, it could not be placed on a table. It came with clouds, thunder, heat, and sudden light. It could split trees, set buildings aflame, kill animals, and leave human beings staring upward at a sky that seemed alive with power. It is easy to understand why many cultures placed lightning close to God's spirits, divine weapons, or heavenly anger. The explanation was not scientific in the modern sense, but the emotional response was deeply human. Lightning looked like force without visible machinery. It seemed to fall from a realm beyond ordinary reach. Even today, after centuries of theory, measurement, and engineering, lightning still makes the body pause. It reminds us that electricity is not only the mild service hidden in a wall socket or the soft glow of a screen. It is also a natural force that can gather across clouds and ground, then release itself in an instant. The difference is that modern science has a map. Earlier observers had only the flash. The electric fish offered a stranger and more intimate clue. Certain fish known in the ancient world could produce a numbing shock. This was not lightning above the head. It was a force felt directly through touch. A hand met living flesh, and something invisible answered back. Here was an animal that seemed able to stun without teeth claws or poison. The effect was real, but its cause was obscure. Was it a property of the animal's body, a hidden fluid, a vital force, a medicine, a weapon, or a wonder? The questions could be asked, but not yet answered, through nerves, electric organs, membranes, or voltage. Or, once again, nature gave the sign before the explanation. The lodestone created a quieter wonder. It did not shock or flash. It pulled. Iron moved toward it as if the stone possessed an invisible appetite. Later, magnetism would become one of electricity's great partners, but for early thinkers, magnetic attraction and electric attraction were usually not the same kind of thing. The difference mattered. Amber attracted light objects only after being rubbed. A magnet attracted iron without that preparation. Amber's effect seemed temporary and delicate. Magnetism seemed steady and enduring. The two phenomena resembled each other just enough to invite comparison, but differed enough to keep them apart. For centuries, electricity and magnetism stood near each other without merging. They were neighbors in mystery, not yet members of one household. The slow work of sorting began more clearly in the early modern period, when natural philosophers became increasingly interested in repeating observations and separating one phenomenon from another. This was a crucial shift. Instead of treating every marvel as isolated, they began to ask what belonged in the same category and what did not. William Gilbert, writing around 1600, became one of the important figures in this early sorting of the invisible world. He studied magnetism deeply, especially in relation to the Earth itself, and he also examined the attractive effects produced by rubbed materials like amber. He helped distinguish magnetic attraction from what would later be called electric attraction. That distinction may sound modest, but it was necessary. To understand something, science sometimes has to separate before it can unite. Gilbert did not yet know that electricity and magnetism would one day be joined in a deeper theory. But by noticing their differences clearly, he helped make future understanding possible. Confusion had to be organized before it could be transformed. In this early period, electricity was still mostly an effect of surfaces and touch. A material was rubbed, and it attracted small things. A spark might appear. A body might feel a shock. These were brief phenomena, difficult to sustain and difficult to measure. They did not yet flow steadily through wires. They did not yet power machines. They did not yet light streets or carry voices. Electricity was more like a visitor than a servant. It appeared, startled the observer, and vanished. That made it hard to study. A falling object could be watched again and again. A magnet could be placed near iron and remain active. But static electric effects depended on dryness, friction materials, and careful conditions. One material worked better than another. One day produced stronger effects than another. A spark appeared in darkness, then failed to appear when expected. The phenomenon seemed almost moody, not because nature lacked order, but because experimenters did not yet know which conditions mattered. This was not yet the clean science of circuits and equations. It was a science of tables, cabinets, rods, cloth, dry rooms, and repeated disappointment. It belonged to people trying to make a strange effect appear reliably enough to compare, describe, and share. The language was still forming. Some imagined invisible emissions from objects. Others spoke of subtle fluids. Others compared electric attraction to magnetism, even when the comparison did not fully work. These early models were not modern, but they were not useless. They gave experimenters a way to ask questions. A wrong picture can still guide the hand toward a better test. That pattern will return again and again. Human beings rarely stepped from darkness straight into truth. They made temporary images, fluids, fires, effluvia, animal forces, hidden tensions. Then they tested those images against what the world actually did. When the image failed, it sometimes showed where the next question should begin. In the case of electricity, one of the first great problems was that the phenomenon had no stable presence. It could be made in small bursts, but not kept. A rubbed object might attract for a while, but the effect faded. A spark might leap, but then the moment was gone. If electricity was ever going to be understood deeply, people needed more than surprise. They needed a way to hold the effect long enough to examine it. Before that happened, electricity remained halfway between natural philosophy and wonder. It was studied, but also displayed. It invited serious inquiry, but it also drew crowds. A person could gather observers by producing sparks from a machine, making hair rise, or delivering a harmless but memorable shock. Spectacle could blur the line between experiment and entertainment, and yet even spectacle had value. It made invisible force social. It allowed many people to feel the same phenomenon at once. It spread curiosity beyond a few scholars. It created a culture in which spark shocks and charged bodies became familiar enough to be questioned. Wonder, in this case, did not oppose knowledge. It prepared people to care. Still, the deeper questions remained. What was being moved? Where did it come from? Why did rubbing matter? Why did some materials attract while others did not? Why did a spark leap through air? Why could a shock pass through a body? Why did lightning look like the greatest spark imaginable, yet remain beyond human reach? The questions gathered faster than the answers. Before electricity could be measured, it had to be noticed. Before it could be named, it had to be separated from other marvels. Before it could be unified with magnetism, it had to be distinguished from magnetism. Before it could become technology, it had to become a repeatable phenomenon in the hands of people willing to try again after uncertain results. There is a quiet beauty in that. The modern world makes electricity feel obedient. We press a switch and a room fills with light. We plug in a device and energy flows without drama. We send messages across oceans without seeing the forces that carry them. Electricity has become so ordinary that it almost disappears from attention. But in the beginning, nothing about it felt ordinary. A rubbed piece of amber suggested that matter had hidden moods. A fish blurred the line between life and invisible force. A lodestone made stone seem active. A storm revealed a power so large that human beings could only watch and wonder. The story had not yet found its thread. It was waiting in fragments in the small pull of dust toward amber, in the numbed hand of someone touching an electric fish in the compass needle's ancestor, in the flash over a dark horizon. Each fragment was real. Each carried a part of the future, but no one yet saw the whole shape. That is why before electricity had a name means more than a missing word. It means before electricity had a stable identity in the human mind. Before it was charge current field wave or power. Before it was linked to magnetism, chemistry nerves, light, and machines. Before it became the hidden architecture of modern life. In that earlier world, electricity was not yet one thing. It was a set of encounters, a pull, a shock, a flash, a numbness, a spark, a strange attraction in dry air, a heavenly fire that answered no human command. Because it was not yet one thing, the path forward required patience. People had to collect the encounters and compare them. They had to separate effects that only seemed alike and bring together effects that seemed unrelated. They had to invent tools, words, and habits of experiment. They had to accept that the first explanation might be wrong, but still worth testing. By the time experimenters began building machines to generate stronger static charges, electricity had already moved beyond simple wonder. It was still mysterious, but no longer only a marvel. It was becoming something that could be produced under controlled conditions, intensified, shared, and tested. That shift leads directly to the next great step. If electricity could be generated, perhaps it could be stored. If a spark could be produced, perhaps a stronger shock could be held in waiting. If the invisible force vanished too quickly, perhaps some clever arrangement of glass, metal, and liquid could trap it long enough for human beings to study it. The early world had seen electricity appear and disappear like a ghost. Soon someone would try to put the ghost in a jar. The first great step toward understanding electricity was not a theory. It was a shock. In the middle of the 18th century, in rooms filled with glass rods, metal chains spinning machines, curious observers, and the dry crackle of static charge electricity began to change its character. It was no longer only something that appeared for a moment and vanished. It was no longer merely the brief attraction of rubbed amber or the tiny spark from a charged object. For the first time, people began to believe that electricity might be collected, held, and released. That belief gathered around a simple object, a glass jar. The Leyden jar did not look like the beginning of a new electrical age. It did not move. It did not glow steadily like a lamp or turn like a motor. It was a container, a little arrangement of glass metal and conductive material, quiet on the table, until someone completed the path between its inner and outer surfaces. Then the invisible force made itself known. A person touched it and felt a sudden jolt through the body. The shock could startle, frighten, amuse, or impress a roomful of observers. It proved in a way no delicate attraction of dust could prove that electricity had force. Earlier static experiments had been fragile and temporary. A rod rubbed with fur could attract light objects, but the effect faded. A spark could be drawn, but it disappeared in an instant. Electrical machines could produce charge, but the charge seemed restless, difficult to keep, always slipping away from the moment of observation. The jar promised something different. It suggested that electricity could wait. This was not storage in the modern sense of a battery. The Leyden jar did not create a continuous current that could power a long experiment. It accumulated static charge and released it suddenly. But even that was revolutionary. The jar turned a momentary effect into a prepared event. A spark could now be held in silence. Imagine an 18th century room, the air dry, the observers gathered close, the apparatus arranged with care. A glass jar sits on the table, ordinary in shape, but charged with expectation. Nothing about its stillness tells the eye what it contains. The danger has no color, no weight, no smell. Then a hand reaches out, the body becomes part of the circuit, and the jar answers. It is easy to see why such demonstrations fascinated people. Electricity until then had often felt like a natural curiosity. With the Leyden jar, it became social, repeatable, and dramatic. It could be carried into lecture rooms. It could be shown to audiences. It could be passed through chains of people holding hands so that a whole group might jolt together. Wonder became communal, but the wonder also concealed confusion. The jar worked before anyone fully understood why it worked. People could charge it, discharge it, and feel its power. But the exact nature of what was being stored and where it was being stored remained uncertain. Some early experimenters thought the water inside the jar was essential. This was understandable. Early versions often involved water or another conducting material inside the glass container with a metal contact leading into it. If the jar delivered a shock, perhaps the electrical substance was somehow being held in the liquid. It was a reasonable mistake. The liquid was visible. The shock was not. When human beings do not yet understand an invisible process, they often attach explanation to the visible thing closest to it. The water seemed like the home of the mystery because it could be seen, touched, poured, and named. So the first explanation settled on the wrong part of the apparatus. But that wrong explanation could be tested. Experimenters altered the jar. They changed its contents. They changed the surfaces. They changed how it was held, lined, touched, and connected. Slowly, the important arrangement became clearer. The key was not simply liquid inside a vessel. The key involved two conducting surfaces separated by an insulating layer of glass. Opposite charges could accumulate on the two sides of the glass, unable to pass directly through the insulator, but ready to rush together if given a path. The modern explanation would come later with more precise language. Capacitance, conductors, insulators, potential difference, electric fields. These were not the words with which the earliest users understood the jar. But the experimental lesson began to emerge before the full vocabulary. The jar was not a bottle filled with electrical fluid. It was a relationship between surfaces. This shift was subtle but profound. Electricity was beginning to be understood less as a mysterious substance, placed somewhere, and more as a condition created between things. The power of the jar did not belong simply to one object inside it. It belonged to separation, arrangement, tension, and the possibility of sudden connection. Science often advances this way. A device works first, then people use it, explain it badly, repeat it, modify it, and slowly discover the principle hidden inside the working object. The Leyden jar was a teacher because it shocked the hand, but also because it shocked the explanation. It refused to be understood too simply. The jar also made electricity feel more dangerous. A rubbed piece of amber was delicate. A spark from a small object might startle, but only briefly. A charged Leyden jar could produce a stronger shock, strong enough to make people recoil, shout, laugh, nervously, or fear that something serious had happened inside the body. This bodily experience mattered. Electricity was not only seen, it was felt. When a person received a shock, the invisible force crossed the boundary between object and self. It entered the nerves, muscles, and imagination. It suggested that electricity might have some relation to life, motion, pain, and vitality. Later, that suggestion would become central in the story of Galvani and the twitching frog leg. But already with the Leyden jar, the body was becoming part of electrical knowledge. The human hand was an instrument before the voltmeter. People learned by touching what they did not yet understand. Today, electrical safety depends on not becoming part of the circuit. We build insulation, grounding breakers, warnings, and distance around electricity. But in the 18th century, part of the fascination was precisely that electricity could be brought into the body and felt directly. The shock inside the jar gave certainty of a kind. It told everyone in the room that something real had been collected. Yet certainty about reality did not mean certainty about meaning. The jar could prove that electricity had been stored, but not exactly what electricity was. It could show that charge could be accumulated, but not yet explain charge in the modern sense. It could produce spectacular evidence, while interpretation still struggled behind it. Again and again, people learn to do something before they understand what they are doing. They make electricity, attract spark shock travel, bend a needle, move a machine, and light a city. But each success brings a new misunderstanding with it. Some imagined electricity as a subtle fluid. Others debated whether there were two electrical fluids or one. Some thought in terms of excess and deficiency. These models were not modern, but they gave shape to observation. They allowed people to speak of charge, moving, accumulating, discharging, and balancing. The language was imperfect, but useful. Wrong ideas are not all equal. Some wrong ideas block inquiry by pretending to explain too much. Others help inquiry by making a vague mystery testable. The fluid models of electricity did not capture the modern reality of charge and field, but they gave experimenters a practical way to think about storage and discharge. The jar also changed the scale of experiment. Sparks could become larger. Shocks could become more memorable. Multiple jars could be connected together, creating stronger discharges. What had once been the small attraction of light objects became an experimental force capable of startling a whole room. The more powerful the effect became, the more urgent the questions became. What was being stored? How much could be stored? Why did glass matter? Why did metal matter? Why did holding the outside of the jar change the result? Why did the discharge require a path between two separated states? The jar forced questions through sensation. In one sense, the Leyden jar was a machine for making ignorance undeniable. It allowed people to create an effect strong enough that it could not be dismissed as a small curiosity of amber or friction. Anyone who felt the shock knew that something had been concentrated. Because the answer was not yet clear, experiment multiplied. The Leyden jar marks the moment when electricity becomes not just an event, but a stored possibility. Before the jar, electricity often seemed like a fleeting behavior of rubbed materials. After the jar, it could be accumulated, transported, displayed, compared, and intensified. It became more available to thought. Yet the jar also kept electricity within the world of sudden release. It could hold charge, but it could not make electricity flow steadily like water through a channel. Its power came in a burst. The shock was brief, brilliant, and finished. After discharge, the jar had to be charged again. This limitation would matter later. For now, the jar gave experimenters a new kind of control, but not the kind of control that would build the electric world. It gave them stored static electricity, not continuous current. It offered a spark, not a sustained flow. It intensified the mystery, but did not yet turn electricity into a lasting tool. Still, that was enough to change imagination. Once electricity could be stored in a jar, it became easier to imagine that the same force might exist elsewhere in greater forms. The little spark on the table began to resemble the great spark in the clouds. The laboratory and the storm started moving closer together in thought. If a jar could hold a shock, what was a thunder cloud holding? The question led naturally toward lightning. It led toward the idea that the terrifying flash across the sky might not be separate from the sparks produced by human apparatus. The Leyden jar made that comparison feel possible because it gave people a miniature version of sudden electrical release. The jar was in a sense a storm reduced to a handheld object. That image is not exact science, but it captures the emotional movement of the time. People were beginning to see continuity between the small and the immense. A spark from a machine, a shock from a jar, and lightning in a storm might belong to the same natural family. But resemblance was not proof. The next stage would require a more dangerous question. Could the electricity of the laboratory and the lightning of the sky be shown to be the same? Could the heavens be brought into experiment? Could a storm become part of natural philosophy, rather than only an object of fear? As this section closes, the jar rests again on the table. Its charge has been spent. The room has settled. The observers step back, perhaps laughing, perhaps shaken, perhaps already reaching for another test. Outside, beyond the glass metal and human curiosity, another electrical mystery waits on a scale no jar can contain. Clouds gather above the rooftops. The air begins to charge. Somewhere in the darkening sky, the question that began inside a small glass vessel rises toward the storm itself. Outside the room of glass jars and charged machines, the older mystery still waited above the rooftops. Lightning had always belonged to the sky. It came with clouds, thunder, wind, and sudden brightness. It could strike a tree and split it open. It could set a roof on fire. It could kill a person or animal in an instant, leaving behind silence and the feeling that something beyond human reach had passed through the world. For centuries, lightning did not need a scientific explanation to be powerful. It had already entered religion, myth, poetry, and ordinary dread. It seemed to fall from the heavens with intention. Even when people did not explain it as divine anger, they could still feel that lightning belonged to a scale far beyond the sparks drawn from rubbed amber or laboratory machines. But by the 18th century, the small spark and the great flash had begun to resemble each other. In lecture rooms and private studies, experimenters watched electricity leap across tiny gaps. They heard the crack of discharge. They felt shocks pass through bodies. The Leyden jar showed that electricity could be gathered and released suddenly with enough force to startle a room. The spark from a charged machine was tiny compared with lightning, but the likeness became difficult to ignore. Perhaps lightning was not a separate heavenly fire. Perhaps it was electricity on a vast natural scale. This was a dangerous idea in more than one sense. It did not merely challenge old explanations. It invited human beings to bring storms into the realm of experiment. If lightning and laboratory sparks belong to the same natural phenomenon, then the sky itself might be tested. The cloud could become part of the apparatus, but this apparatus had no walls, no reliable control, and no mercy for carelessness. Benjamin Franklin stands near the center of this story, though not as the simple lone hero of legend. Franklin had been thinking deeply about electricity, especially charge-discharge pointed conductors, and the possibility that electrical fire could move between bodies. He proposed that lightning might be electrical, and that a pointed rod could draw electrical fire from a cloud. The idea was bold, but it did not emerge from nowhere. Sparks, shocks, Leyden jars, and charged objects had prepared the mind to see the storm differently. Franklin worked inside a growing network of electrical experiment, one that crossed the Atlantic through letters, proposals, replications, and demonstrations. The story is more interesting when we see that network, rather than only a single figure under a storm. The famous kite experiment has become one of the most familiar scenes in science. A man, a boy, a kite, a key, a stormy sky. The image is so vivid that it almost overwhelms the history. It is often told as if Franklin simply flew a kite into lightning and discovered electricity in a single dramatic instant. But that version is too clean and in some ways too dangerous. Franklin did not discover electricity. Electricity had already been studied for generations. He did not invent the connection between sparks and lightning from nothing. What he helped show was that the electricity of the laboratory and the electricity of the storm could be linked. The details matter. Franklin's kite was not meant to be struck directly by lightning in the way popular imagination sometimes suggests. A direct strike would likely have killed him. The point was to draw charge from the storm cloud through the wet string so that a key attached to the line could produce electrical effects. Sparks could be drawn. A Leyden jar could be charged. The cloud's electricity could be made to behave like electricity already known in experiments. In that moment, the sky was no longer only spectacle. It had become evidence. Franklin was not alone in this movement. In France, Thomas-François Dalibard performed a related experiment with an elevated iron rod before Franklin's kite experiment became famous. Dalibard's work helped confirm that charge could be drawn from a storm cloud. This matters not to diminish Franklin, but to restore the shape of discovery. Science rarely changes because one mind stands alone under the sky. It changes when an idea becomes testable by more than one person in more than one place under conditions that allow nature to answer again. Still, the emotional power of Franklin's story remains. A storm approaches. The air grows heavy. The ordinary world darkens. A kite rises into the charged atmosphere, not as a toy, but as a fragile bridge between human curiosity and the clouds. A key hangs from the line. The string becomes damp. The invisible tension gathers. Then the spark appears. Small, controlled, and human-sized. It is not the lightning bolt itself, but it is enough. The sky has touched the experiment. A force that once seemed to belong entirely to distance and terror has entered the scale of the hand, the key, the jar, the observable spark. That was the transformation. The storm did not become safe. It did not become fully understood, but it became part of natural philosophy. Lightning had not lost its danger, but it had lost some of its isolation. It could be compared, tested, guided, and partly defended against. The same force that had once seemed like a sudden weapon from the sky could be invited toward metal, drawn along a path, and carried into the ground. From this insight came the lightning rod. The lightning rod is easy to underestimate because it is so practical. A metal rod rising above a building connected down toward the earth does not look as mysterious as a spark from a cloud or a charged jar in a lecture room, but its meaning was profound. It showed that understanding electricity did not only satisfy curiosity, it could change how people lived with danger. A building could be given a safer path for the storm's discharge, not stopping lightning, not commanding the sky, not defeating nature, simply offering the force a route less destructive than wood roof chimney or human body. Even here, trial and error continued. Lightning rods carried scientific, practical, and cultural controversy. Some people doubted them. Some feared they might attract lightning rather than protect from it. Some debates turned on the shape of the conductor, pointed or blunt, and on how best to install the device. Others were cultural or religious because redirecting lightning touched older feelings about divine power, fate, and human interference with the heavens. A simple metal rod became a symbol of a changing world. But the cost of this new relationship with lightning could be severe. The danger was not abstract. Georg Wilhelm Richmann, a scientist in St. Petersburg, was killed in 1753 while investigating atmospheric electricity. He had been using an apparatus connected to a rod during a thunderstorm when a discharge struck him. His death became a grim warning that the boundary between experiment and exposure had become dangerously thin. Electricity had entered the body again, but this time not as a controlled shock from a jar. It came with lethal force. Richmond's death belongs inside the story because it prevents the history from becoming too triumphant. The 18th century effort to understand electricity was not a smooth march from ignorance to control. It was risky, uncertain, and sometimes fatal. People were learning how to test a force before they had learned how to protect themselves from it. The sky had become an experiment, but not a tame one. There is a quiet tension in this stage of electricity's history. On one side, experiments were reducing mystery. Lightning was becoming part of the same electrical world as sparks jars and charged bodies. On the other side, the force remained vast, sudden, and indifferent. To understand that lightning was electrical did not make it gentle. It only made its danger more intelligible. Science does not always make the world less frightening by making it less powerful. Sometimes it makes the world more understandable while leaving its power intact. A storm after Franklin is not weaker than a storm before Franklin. A lightning strike is not less violent because it can be described electrically, but the human relationship to it changes. Fear can begin to include method. The goal was not to drain the sky of wonder. It was to create a path between wonder and understanding. A person could still stand beneath dark clouds and feel awe, but now that awe could be joined by questions about charge, conduction points, paths, and discharge. Yet the deeper nature of electricity remained unsettled. Was it one fluid or two? Was it something that flowed from excess to deficiency? Was it a kind of fire? How did it move through metal? Why did points matter? Why did air sometimes block it and sometimes allow a spark to leap? Why could the same force appear as attraction, shock, spark, and lightning? The experiments had answered one great question and multiplied many others. Franklin's age also teaches us something about scale. A small spark on a table and a lightning bolt in a storm are not equal in force, but they can belong to the same natural order. This is one of science's great achievements, to recognize likeness across scale. Once that connection was made, the imagination of electricity expanded. It was no longer only an odd attraction produced by rubbing. It was no longer only a shock trapped in a jar. It was now a force that could span the tiny and the immense, the parlor demonstration and the thundercloud, the fingertip and the horizon. Still, electricity remained mostly sudden. The jar discharged in a burst. Lightning struck in an instant. Sparks appeared and vanished. Even when electricity had been connected to the sky, it had not yet been turned into a steady flow. It could shock, flash, and protect buildings through a path to ground, but it could not yet run continuously through an apparatus for as long as the experimenter wished. A sudden discharge can reveal power, but a continuous current can reveal behavior over time. With a current, one can heat wires, decompose chemicals, magnetize materials, test conductors, and build instruments that depend on sustained flow. The science of electricity needed more than sparks. It needed persistence. The sky could not provide that persistence on command. A storm came when it came. Lightning struck where conditions allowed. Even the best atmospheric experiment depended on weather danger and chance. The electricity of the sky was magnificent, but it was not obedient enough to become the everyday engine of experiment. The next breakthrough would come from a place far smaller than the sky, not from clouds, but from flesh. A frog's leg on a table would twitch in response to metal contact and hidden electrical conditions. To one observer, this movement would seem to reveal an electricity belonging to the living body itself. To another, it would point towards something outside the animal, something in the contact between different metals and moist tissue. The storm had shown that electricity could belong to the heavens. The frog would suggest that it might belong to life. Between those two ideas, another question would slowly take shape. Could electricity be made to flow continuously, not as a flash, not as a shock, not as a moment of violence, but as a steady current that could be studied, used, and followed wherever it led? After the storm, the story of electricity moves somewhere quieter. Not to the open sky, not to a rooftop, not to the violence of thunderclouds, but to a table where the body of a frog lies prepared for experiment. The scene is smaller, almost unsettling in its stillness. A metal instrument touches tissue. A nerve is disturbed. Suddenly, a dead limb moves. The leg twitches. To an 18th century observer, this was not just a mechanical detail. It was a sign that electricity might belong not only to amber jars, wires, or storms, but to life itself. The force that had shocked the hand and flashed in the sky now seemed to be hidden inside muscle nerve and living flesh. This is why Luigi Galvani's frog experiments became so powerful in the history of electricity. They did not begin as a clean path toward the battery. They began with a mystery at the border between physics and life, a body that should have been still moved when metal touched it. The movement was brief, but the implication was enormous. Perhaps animals carried their own electricity. Galvani was not foolish for thinking this. Electricity had already shown that it could enter the body. The Leyden jar could jolt a person's muscles. Electrical demonstrations made bodies jump, hair rise, hands pull back, and crowds laugh nervously at a force they could feel but not see. If electricity could make living bodies move from outside, perhaps life itself contained an electrical principle within. The frog leg seemed to offer evidence. Galvani observed contractions when the nerves and muscles of dissected frogs came into contact with metal under certain conditions. Sometimes the effect appeared in the presence of electrical machines or atmospheric electricity. Sometimes it appeared through contact between different metals and the animal tissue. Each twitch seemed to ask the same question. Was this electricity inside the animal released by contact, or was the animal only revealing electricity produced somewhere else? At first, the question was hard to answer. The frog was both object and instrument. It was not merely being tested, it was also detecting something. Its nerves and muscles responded with visible motion, making the invisible force legible in the most intimate way possible. The effect touched the imagination as much as the intellect. Here was electricity no longer outside the body, but seemingly woven into the body's machinery. It suggested that life might depend on hidden currents, that nerves might carry something like electrical fire, that the difference between living motion and dead stillness might be understood through the same force that cracked in jars and clouds. This was a seductive idea. It also contained a truth, though not exactly in the way Galvani first imagined. Modern biology does recognize electrical signaling in nerves and muscles. Living cells maintain electrical differences across their membranes. Nerve impulses and muscle contractions depend on electrical and chemical processes. In that broad sense, the body is indeed an electrical organism. But Galvani's frog leg was not only showing animal electricity, it was also showing the effect of metals, moisture, and contact. That difference would matter enormously. Alessandro Volta, watching and thinking through Galvani's results, began to doubt the interpretation. To Volta, the source of the electricity was not necessarily inside the animal. He suspected that the contact between different metals played a crucial role. The frog tissue in this view was not the source of the force. It was the sensitive detector. This disagreement became one of the most productive arguments in science. Galvani saw the frog as revealing the electrical nature of life. Volta saw the frog as responding to electricity generated by the arrangement of materials. One interpretation looked inward toward the animal body. The other looked outward toward metal liquid and contact. Both were responding to the same twitching leg, but they were building different worlds from it. The story could have remained a dispute over interpretation. Instead, Volta tried to remove the frog. That was the crucial move. If the animal was only a detector, then perhaps electricity could be produced without the animal at all. Perhaps different metals separated by moist material could generate the effect by themselves. Perhaps the frog leg had been a dramatic witness to a process that did not require living tissue. Volta began arranging metals and conductors in new ways. Copper and zinc, or other pairs of different metals, were placed with moist materials between them. Layer by layer, disc by disc, the apparatus grew into what became known as the voltaic pile. It looked almost modest, alternating pieces of metal separated by cardboard or cloth soaked in salt water or another conducting solution. But unlike the Leyden jar, it did not merely store a sudden shock. It produced a sustained current. The Leyden jar made electricity wait, then release itself in a burst. The voltaic pile made electricity continue. It allowed experimenters to work not only with sparks and shocks, but with a flow that could be maintained long enough to test, observe, and transform matter. A spark is dramatic, but brief. A shock convinces the body, but then it is gone. Lightning overwhelms the senses, but cannot be summoned safely at will. A continuous current is quieter in the first instant, but far more revolutionary. It gives time to the experimenter. With time, electricity can be followed. It can pass through wires, through solutions, through instruments. It can produce chemical changes. It can heat, decompose, attract, repel, and later magnetize. It can be connected, interrupted, measured, compared, and repeated. The current turns electricity from a sudden visitor into a steady presence in the room. Volta's pile did not explain everything. It did not give a modern theory of electrochemistry all at once. It did not reveal electrons, ions, or the full chemical processes at work. But it gave science a new source of electrical action, one that did not depend on friction weather or the brief discharge of stored static charge. The experimenter could now begin again whenever needed. This changed the rhythm of electrical science. Earlier work had often depended on building up charge, waiting for conditions, rubbing materials, turning machines, or gathering storms. Now, with a pile of metal discs and moist separators, a current could be created on the table. It was not yet the electric world of power stations and wires across cities, but it was the first step toward electricity as a sustained tool. And it came from an argument over a twitching frog. A question about life helped create a device that transformed physics and chemistry. Galvani's interpretation may not have fully explained the source of the current in the way Volta argued against, but without Galvani's observations, Volta's response might not have taken the form it did. An incomplete idea opened the path to a new instrument. Galvani did not simply fail. He saw something real, named it, through the best conceptual frame available to him, and placed it before the scientific world. Volta then challenged that frame and built an apparatus to test a different explanation. The disagreement mattered because it moved from words into objects. It became a pile of metal. Volta's pile gave nature a new voice. The current it produced became a gateway into discoveries no one could have reached with static electricity alone. It opened the way for electrolysis, the breaking apart of compounds through electric current. It helped scientists explore the relationship between electricity and chemical change. It allowed experimenters to ask whether electricity was not merely an effect of matter, but a force capable of rearranging matter. Electricity had moved from attraction to storage, from storage to lightning, from lightning to life, and now from life into chemistry. The same hidden force that had seemed to live in the storm in the animal body could now be made to act inside liquids and compounds. Yet the deeper meaning of the current was still not clear. What exactly was moving through the circuit? Was it a fluid, a tension, a chemical action carried through metal? Why did different metals matter? Why did the moist layer matter? Why did the arrangement need a closed path? Why did the current weaken, and how could it be strengthened? The new device answered one question by creating many more. The Leyden jar had been theatrical. It gave a sudden shock good for demonstrations and astonishment. Lightning had been sublime and dangerous. Galvani's frog had been eerie, making electricity seem connected to the secret boundary between life and death. The voltaic pile was different. It was patient. It could sit on a bench and produce current steadily enough for repeated work. It did not need to frighten a crowd to prove its importance. It did not need to split a tree or make a dead limb twitch. Its power was in continuity, and continuity allowed science to deepen. Before it, electricity is mostly a matter of moments. After it, electricity becomes something that can be sustained and directed. The story shifts from spark to current. The shift also changed how experimenters thought about circuits. A current needed a path. It was not enough to have charged objects or sudden contact. The circuit had to be completed. Materials mattered. Connections mattered. Interruptions mattered. Electricity became less like a mysterious leap and more like a movement through an arranged system. That arrangement would become the foundation for later electrical technology. At the time, it still felt experimental and uncertain. The current from early piles could be unstable. The materials could corrode. The strength of the effect depended on construction. The chemical processes were not yet fully understood. Devices improved through repeated adjustment, comparison, and failure. Even the invention that gave electricity continuity was imperfect. Volta did not hand the world a finished modern battery. He gave it a principle, an apparatus, and a new kind of electrical source. Others would modify, improve, and reinterpret it. The battery would become more reliable over time, but only through more trial and error. Still, the change was irreversible. Once continuous current existed, electricity could no longer be studied only as static charge. It could be made to flow, and flowing electricity behaved in ways that static electricity had not revealed clearly. It could interact with chemicals. Heat wires produce magnetism and later power devices. The current became the thread that pulled separate phenomena into one expanding fabric. The frog leg had twitched and the world had moved. There is another quiet lesson in the Galvani and Volta story. Two scientists can look at the same phenomenon and both see something important, while neither sees the whole future. Galvani's attention to the animal body pointed toward bioelectricity. Volta's attention to metals and contact pointed toward battery circuits and electrochemistry. The disagreement did not produce one winner and one worthless error. It produced branching paths. The twitching frog leg remains unforgettable because it sits between worlds. It belongs to life but leads toward machines. It belongs to anatomy but opens electrochemistry. It belongs to a mistaken debate but helps produce one of the most useful devices in science. Volta's pile made the next century possible. With continuous current, experimenters could ask new questions with a steadiness that earlier electrical science lacked. They could place wires near instruments and watch small deflections. They could send current through solutions and observe chemical change. They could create repeated effects without waiting for static charge or thunderstorms. The current did not yet explain itself, but it made itself available. That availability is the bridge to what comes next. Because once electricity could flow continuously through a wire, the wire itself became an object of mystery. Was the current confined inside the metal? Did it act only along the path it traveled? Or did something around the wire change as well? For a long time, electricity and magnetism had stood near each other without fully merging. Amber attracted, lodestone pulled iron, sparks shocked, magnets turned needles. They seemed like separate marvels, related perhaps by analogy, but not by mechanism. The continuous current would disturb that separation. A wire carrying current would be brought near a compass. The compass needle, loyal for centuries to Earth's magnetic direction, would shift. Not violently, not with the drama of lightning, not with the shock of a jar, not with the eerie twitch of a frog's leg. Just a quiet turn. But that small movement would open a new world. It would suggest that electricity was not only a flow through matter, it could reach into the space around itself. It could create a magnetic effect. It could touch a compass without touching it. The frog had shown that electricity could make muscle move. Soon, the compass would show that electricity could make magnetism move too. The next great shift in the history of electricity began with almost no drama. No thundercloud split open. No jar shocked a crowded room. No frog's leg twitched on a table between life and death. There was only a wire, a current, and a compass needle that moved when it was not supposed to move. For centuries, the compass needle had seemed to belong to another order of nature. It pointed north because the earth itself acted like a great magnet. Sailors trusted it across dark waters. Travelers watched it steady itself after disturbance. Magnetism was quiet, directional, and ancient, a force that pulled iron and guided navigation long before anyone knew that electricity might be connected to it. Electricity still felt restless by comparison. It sparked, shocked, accumulated, discharged, and now after volta flowed through a circuit. It could be produced by chemical arrangements and sent along wires. It could pass through liquids and cause chemical changes. But in many minds, it still belonged to its own world. Then the compass needle turned. Hans Christian Ørsted, working in Copenhagen in 1820, noticed that when an electric current passed through a wire near a compass, the needle was deflected. The movement was small, but the implication was enormous. A current in a wire was somehow producing a magnetic effect around it. The wire had not touched the needle. The current had not flowed through the compass. Something in the space around the wire had changed. Electricity was no longer only something inside a circuit. It seemed to reach outward. A hidden relationship existed between a moving electrical current and a magnetic needle, a relationship that could not be explained by treating electricity and magnetism as separate curiosities. The compass did not simply move. It disturbed an entire map of nature. Like many scientific turning points, the scene is simple only from a distance. It is easy to imagine the discovery as one clean demonstration, a wire near a compass, a closed circuit, a swinging needle. But Ørsted had long suspected that electricity and magnetism might be related, influenced by broader ideas about unity in nature. The observation mattered because it gave experimental weight to that suspicion. A hope became a visible movement. Even then, discovery was not only about seeing, it was about recognizing that the movement mattered. A compass needle can move for many reasons. A table can shake. An instrument can be placed carelessly. A magnetic object can be nearby. A weak deflection might be dismissed as nuisance or error. Ørsted followed it. He showed that the direction of the needle's deflection depended on the direction of the current. This was not random disturbance. It had order. The current and the needle were linked by a pattern, and the pattern could be repeated. Repeatability made the tiny movement dangerous to old assumptions. Until then, electricity and magnetism had stood near each other in human curiosity, but not fully together in theory. Gilbert had carefully distinguished them in the early modern period, and that separation had been useful. Amber's attraction was not the same as the steady pull of a lodestone. Electric effects and magnetic effects behaved differently, and confusing them too quickly would have clouded the evidence. Science sometimes has to separate before it can reunite. By 1820, the separation had become too small to hold. The voltaic pile had given experimenters continuous current, and continuous current revealed a behavior that static sparks had not made clear enough. When electricity flowed steadily, magnetism appeared around it. The relationship had been waiting for the right kind of electricity. A spark was too brief, a charged object too temporary, a laden jar too sudden in its discharge. But a sustained current could sit beside a compass long enough for the needle to respond. Volta's battery, born from the argument over frog legs, made Ørsted's observation possible. One mistake produces a tool. The tool produces a new effect. The new effect breaks an old boundary. Galvani's animal electricity did not become the final explanation, but the debate led to Volta's pile. Volta's pile made continuous current available. Continuous current let Ørsted see electricity touching magnetism. The story advances because errors leave instruments behind. Ørsted's discovery spread quickly through European science. Once the connection was announced, other researchers began trying to understand and extend it. Among the most important was André-Marie Ampère, who responded with extraordinary speed. If a current could affect a magnetic needle, perhaps currents themselves could interact with one another. Perhaps magnetism could be understood in terms of electrical currents. Ampère began to develop a new science of electrodynamics. Electricity was no longer just attraction shock or flow. It had direction. It produced forces around itself. Currents could attract or repel depending on their relative directions. Wires carrying currents could behave in ways that resembled magnetic objects. The old image of electricity as a fluid moving through a conductor was not enough. Something about the moving charge, though not yet understood in modern terms, created a magnetic effect in the surrounding space. The wire became more than a pathway. It became the center of an invisible arrangement. To the eye, nothing seemed to surround it, but the compass knew. This is why the compass needle is such a powerful image for a calm documentary. It is small and almost silent. It does not dazzle the senses. It does not shock the body. It does not fill the sky. Yet its movement reveals that the unseen has structure. A wire lies near a compass. The circuit closes. The needle, which had been resting in its familiar direction, hesitates and turns. The motion is slight, but a whole future moves with it. Electromagnets, motors, generators, telegraphs, speakers, transformers, and the field language that will later become central to physics. All of that is still far away, but the first turn has happened. There is also a shadow beside Ørsted's story. An Italian scholar, Gian Domenico Romagnosi, appears to have observed a possible effect of electricity on a magnetic needle earlier, around 1802. But his report did not transform the field. It did not travel through the right networks with enough force, or it did not arrive in a form the scientific community could use. This detail matters gently. It reminds us that discovery is not only seeing, it is also being heard, repeated, and incorporated into a living conversation. A phenomenon can be noticed and still fail to become a turning point if it does not enter the right channels of attention. Ørsted's observation became a turning point because it connected to a ready scientific world. There were batteries, instruments, experimenters, journals, letters, academies, and networks through which a small deflection could become a major event. The discovery arrived at a moment when it could be repeated, extended, and turned into theory. Again, timing mattered. After Ørsted, the idea of electromagnetism began to gather force, If an electric current created a magnetic effect, then magnetic effects could be strengthened by arranging currents in particular ways. Wires could be coiled, currents could be increased, iron could be placed inside coils and made temporarily magnetic. The electromagnet began to emerge not as a magical object, but as a practical consequence of the new relationship. This too required trial and error. Coils had to be wound, materials had to be tested, current strength mattered, battery power mattered, heat resistance, contact, and insulation all became practical concerns. The invisible relationship between electricity and magnetism had to be translated into devices that worked outside the moment of discovery. The discovery opened the door, but it did not build the room. Even the direction of the magnetic effect was strange. It did not point simply toward or away from the wire. The magnetic influence circled the current. This circular relationship was difficult to imagine if one expected forces to act in straight lines between objects. The wire seemed to create a pattern around itself, a rotational order in invisible space. The compass needle could trace that order. Move the compass around the wire, and the direction changes. The current is not merely pushing or pulling in a simple line. It is producing a magnetic arrangement that surrounds it. The space around the wire has become active. That idea required a new imagination. Earlier, electricity had often been thought of as something that resided on surfaces, accumulated in jars, or flowed through conductors. Now the space outside the conductor mattered. Empty-looking air was no longer empty in the same way. It could hold a pattern of influence. The future language of fields had not fully arrived, but the need for it was beginning. The old mechanical imagination struggled. If one object influences another without touching it, what lies between them? Is there a hidden medium, a circulation, a force transmitted through space, a mathematical relationship without visible substance? These questions would grow larger in the hands of Faraday and Maxwell. The needle pointed toward more than north. It pointed toward a missing concept. The emotional shape of this section is quieter than the earlier ones. The Leyden jar was about stored shock. Franklin's storm was about scale and danger. Galvani's frog was about the eerie border between life and electricity. Ørsted's compass is nearly silent. Its drama is intellectual. A needle turns a few degrees. A line on a scale shifts. A spot appears on a plate. These small things become doorways because they do not fit. The compass needle did not fit a world where electricity and magnetism were separate, so the world had to become larger. After volta current had been a sustained flow useful for chemical experiments and electrical investigations. After Ørsted current became a source of magnetism, it did not only do things at the ends of a circuit or inside a solution, it created effects around the path it traveled. This made electricity feel less confined. A current could be hidden inside a wire, yet its magnetic influence could extend beyond the wire. That extension would later make motors possible. It would make telegraphy possible. It would make generators possible once the relationship was reversed and motion through magnetism produced current. But at this point, the reversal was still a question. If electricity could create magnetism, could magnetism create electricity? That question would become Faraday's great field of labor. But before we leave Ørsted's compass, it is worth staying with the new uncertainty it created. The discovery did not simply add knowledge, it unsettled categories. It made electricity and magnetism feel less like separate forces and more like different faces of a deeper process. As the section closes, imagine the compass at rest again. The current is switched off. The needle returns slowly to its ordinary alignment. Nothing in the room looks permanently changed. The wire is still a wire. The compass is still a compass. The table is still quiet. But the categories have shifted. Electricity has reached beyond the circuit. Magnetism has answered. And somewhere in that small exchange, a new question begins to gather strength. A magnet lies on the table. A coil waits nearby. The compass needle has given its hint. Now another experimenter will begin moving things slowly, patiently, trying to discover whether magnetism can call electricity into being. A magnet lies near a coil of wire and nothing happens. That silence matters. After Ørsted's compass needle turned beside a current-carrying wire, it seemed natural to ask whether the relationship could be reversed. If electricity could create magnetism, perhaps magnetism could create electricity. The question had an elegant shape, and many experimenters wanted nature to answer yes. But the first answer often seemed to be no. A magnet resting beside a wire did not simply produce a steady current. A conductor placed near a magnetic object did not automatically become a source of electricity. The reverse effect, if it existed, was harder to catch than expected. The instruments waited. The needles remained still. The arrangements looked promising and produced almost nothing. This is where Michael Faraday becomes central. He did not enter the story by finding an obvious effect where everyone else had been careless. He entered by staying with the failed expectation long enough to learn what was missing. The question was almost right. The apparatus was almost ready. What had not yet been understood was that magnetism alone, sitting still, was not enough. The missing condition was change. A magnet had to move. A current had to begin or stop. A magnetic condition had to alter. A circuit had to feel not merely a presence, but a transition. When the magnetic situation changed even briefly, another circuit could respond with a pulse of current. The answer was not stillness. The answer was motion. Faraday's experiments did not look like the birth of a power station. They looked like careful work with ordinary things: coils of wire, iron rings, magnets, batteries, switches, and sensitive instruments. He watched for small deflections in a galvanometer, tiny movements that told him current had appeared. The signs were often brief. A needle flicked when a circuit opened. It flicked again when the circuit closed. A magnet moved into a coil and the instrument responded. When the magnet stopped, the response faded. The current seemed to appear only at the moment of change. This was electromagnetic induction. Faraday discovered that when the magnetic environment around a conductor changed, an electric current could be induced. The current did not arise from a battery in the usual chemical sense. It did not come from a jar releasing stored static charge. It came from motion, from changing magnetic influence, from the relationship between electricity, magnetism, and movement. The discovery was enormous, but its first signs were small: a moving magnet, a coil of wire, and a needle that shifted for a moment, then rested again. This is why Faraday's work is so narratively powerful. It begins with patience. It begins with a man watching for a faint response, then learning that the response belongs not to the object alone, but to the change in the object's relation to the circuit. The effect did not live in the magnet like a liquid waiting to pour out. It appeared when the magnetic field changed. That distinction opened the future. Before induction, electricity could be produced through friction, stored as static charge, drawn from storms, or generated through chemical batteries. Each method had limits. Friction was unreliable. Jars discharged suddenly. Storms were dangerous. Batteries depended on chemical materials that could be consumed. Faraday showed another possibility: electricity could be generated through motion in a magnetic system. This did not yet create the electric city, but it gave the city its future principle. A moving magnet near a coil could make a current. A moving coil near a magnet could do the same. Mechanical movement could become electrical energy. The force that once appeared as a spark, a shock, or a mysterious current could now be called forth by turning, rotating, pushing, pulling, and changing the arrangement of magnetic influence. Electricity had gained a new source. This is where the birth of modern power begins, quietly on a bench rather than in a city. Not with a glowing skyline, not with turbines roaring in a hall, but with a small instrument responding to a change no eye could see directly. The future was hidden inside a simple motion. A magnet moves and the needle answers. That image contains the generator in miniature. Later, great machines would rotate coils and magnets on a scale Faraday's first apparatus could not resemble. Steam engines, falling water turbines, and engines would supply motion. That motion would be transformed into electrical power. But the principle was already present in the quiet experiment. Changing magnetism could produce current. Faraday had opened the way from electricity as a phenomenon to electricity as a generated resource. The emotional meaning of electricity changed again. Static electricity was sudden. Lightning was overwhelming. The voltaic pile was steady but chemical. Ørsted's wire reached outward toward a compass. Faraday's induction made electricity feel dynamic, something born from movement itself. Electricity was no longer only stored or released. It could be made through motion. Faraday's way of thinking mattered as much as his result. He was not primarily a mathematical theorist. He thought with experiments, diagrams, physical models, and images of invisible influence. He imagined lines of force patterns extending through space around magnets and currents. To some mathematically trained scientists, this language could seem informal, but it gave Faraday a way to picture what the eye could not see. For him, the space around a magnet was not empty. It had structure. Iron filings scattered near a magnet made that structure visible in a rough physical way. The filings arranged themselves in curves, tracing patterns of magnetic influence. Faraday saw these patterns not merely as decorative effects, but as clues. They suggested that forces filled space in organized ways, that the region around a magnet or wire mattered, that action was not simply jumping from one object to another across nothing. This was a deep change in imagination. Earlier models of electricity often leaned on fluids charges, accumulations, or direct attractions. Faraday's experiments pushed toward a world of fields even before the full mathematical language of fields was established. He helped make it possible to think of invisible influence as something spread through space, shaped, directional, and capable of change. The field was not yet Maxwell's field, not yet written in equations. But the idea was beginning to breathe. Faraday's induction also carried a practical lesson about failure. If experimenters had only looked for current from a still magnet near a still wire, they might have concluded that the reverse of Ørsted's discovery did not exist. The effect was real, but it appeared only under the right condition. A steady arrangement remained silent. A changing one spoke. The question was almost right. It only needed motion. Science often advances at this boundary. A wrong expectation does not have to be discarded entirely. It can be adjusted. The search for magnetism producing electricity was not foolish. It was incomplete. Faraday's achievement lay partly in discovering the missing condition that turned a silent arrangement into an active one. The current appeared not from magnetic presence, but from magnetic change. Once that was understood, the world began to look different. Motion itself became electrically meaningful. A rotating device was no longer merely mechanical. A wheel and axle, a turbine, a falling river, a steam engine, any source of motion might someday become part of an electrical system. The boundary between mechanical energy and electrical energy had opened. Of course, Faraday did not build the entire modern electrical grid. He did not suddenly illuminate cities or solve every engineering problem. The path from induction to practical generation required many later inventions, materials, machines, industries, and standards. But his work gave that future its underlying principle. Electricity could be generated, not merely collected. A battery could power experiments, but batteries alone could not easily become the foundation of vast electrical civilization. They were limited by chemistry, cost materials, and exhaustion. Induction offered another route. Keep the motion going, and the current can continue. The source of electricity could now be linked to engines, water wheels, turbines, and eventually power stations. The electric world would not be built only from sparks. It would be built from rotation. This connection between motion and current also opened the path to motors. If motion and magnetism could produce electricity, then electricity and magnetism could also produce motion. The relationship could be reversed, reshaped, and engineered. A current in a magnetic field could create force. Coils could turn. Machines could move. The same invisible relationship could work in both directions. But none of this was obvious at the beginning. It had to be earned through repeated experiment. Faraday's work belonged to a world where small variations mattered. The shape of a coil mattered. The presence of iron mattered. Whether a circuit was open or closed mattered. The speed of movement mattered. Whether a current was starting, stopping, increasing, or decreasing mattered. Each detail could make the difference between silence and signal. In a quiet room, Faraday could test arrangements that did nothing. Then he changed something, and the needle flicked. The flick was brief, but enough. It told him that an invisible transition had crossed from one circuit into another, from motion into current, from magnetic change into electrical response. A lesser observer might have wanted a stronger, steadier effect immediately. Faraday listened to the brief one. Many discoveries do not first appear at full strength. They arrive as small deflections, short pulses, momentary signs. The task is to decide whether the small sign is noise error or the edge of something real. Faraday's induction experiments required that kind of attention. The current was not always continuous at first. It appeared at moments of change. The world was answering only during transitions. The birth of electric power came from learning to notice change. Faraday's work also shifted electricity away from spectacle and toward infrastructure, though the transformation would take time. The Leyden jar had amazed audiences. Franklin's experiments had reached toward the heavens. Galvani's frog leg had disturbed the imagination. Volta's pile had given experimenters a current. Ørsted's compass had opened the link with magnetism. Faraday gave that link a working future. A generator, in its simplest principle, is organized motion inside a magnetic relationship. It takes mechanical energy and turns it into electrical energy. Later engineers would make the devices stronger, more efficient, more durable, and more useful. But the conceptual leap had already happened. Electricity could be produced by arranging motion and magnetism correctly. From here, the modern world begins to come closer. Not yet as streets of lamps and factories driven by motors, but as possibility. The power station is still far away. The domestic switch is far away. The electric tram, the transformer hum, the global grid, all of these are still in the future. But the path toward them has become visible. It runs through a coil and a moving magnet. Faraday stands as a bridge. Behind him lies the long age of sparks, shocks, jars, storms, animals, and batteries. Ahead lies the age of dynamos, motors, electromagnetic fields, equations, waves, and electrical industry. He carries the story from one kind of electricity into another. He helps turn curiosity into power. And yet, even after Faraday, the deeper explanation remained incomplete. His lines of force were powerful images, but images are not a full theory. They helped the mind grasp invisible structure, but they needed a more exact language. The relationship between electricity, magnetism, motion, and space still had to be written in a form that could reveal what the eye and hand could not. Faraday gave the world experiments and vision. Someone else would give that vision its mathematical architecture. This is where the story begins to move toward James Clerk Maxwell. Maxwell would take Faraday's field intuition seriously, not as a vague metaphor, but as the beginning of a new way to describe nature. He would show that changing electric and magnetic fields could sustain one another, traveling through space as waves. And then the great surprise would come. Those waves moved at the speed of light. The story that began with amber jars, storms, frog legs, batteries, compass needles, coils, and magnets was about to include light itself. A magnet moves through a coil. A needle flickers. The sign is small, but the future is immense. Electricity has learned a new form of obedience, not through command, but through relationship motion, to magnetism, magnetism, to current, current, to motion, again. Electricity is no longer only something found. It is something that can be made. And once human beings learned that, the next question became larger than any single apparatus. What exactly was this invisible structure that allowed electricity and magnetism to call one another into being? Was it a force, a field, a pattern in space, a wave waiting to be understood? Faraday had shown the shape with his hands. Maxwell would try to give it a language. Faraday had given electricity and magnetism a new shape in the imagination. He had not made them visible in the ordinary sense. No human eye could look into empty air and see the pattern around a magnet, a current, or a charged body. But through iron filings, coils, needles, sparks, and movement, he had shown that space itself seemed to matter. Something existed around electrical and magnetic objects, not as a solid thing, not as a visible material, but as an organized region of influence. He called attention to lines of force. Those lines were not decorations, they were a way of thinking. They allowed the mind to imagine that forces did not simply leap from one object to another across emptiness. They filled the space between. They had direction, tension, arrangement, and change. Faraday did not need a polished mathematical language to feel that this picture was important. His experiments told him that the invisible world had structure. But science needed more than a picture. It needed a language precise enough to carry that structure beyond one person's intuition. It needed a way to describe how electric and magnetic effects changed in space and time, how one could give rise to the other, and how the two together might belong to something deeper than either alone. Faraday had shown a set of living relationships. James Clerk Maxwell would try to write those relationships into mathematics. This was not a simple translation. Faraday and Maxwell were different minds. Faraday worked with apparatus touch motion and physical imagination. He thought through experiments and images. Maxwell was trained in mathematics, able to take scattered experimental laws and search for the pattern underneath them. Where Faraday saw lines of force bending through space, Maxwell saw the possibility of a system. The beauty of this moment is that neither kind of mind was enough by itself. Without Faraday, Maxwell would not have had the same field picture to develop. Without Maxwell, Faraday's field intuition might have remained powerful, but incomplete a set of images and experiments without the full mathematical architecture needed to show their reach. The history of electricity needed both the hand and the equation. It needed the coil and the page. Maxwell took seriously the idea that electric and magnetic fields were not merely convenient ways of describing forces between objects. They were part of the physical story. He gathered earlier work by Coulomb-Ampère Faraday and others, then reshaped the subject into a deeper framework. The result was not just a better summary of known facts. It revealed something new. Changing electric fields and changing magnetic fields could sustain one another. Electricity and magnetism were no longer only connected effects seen in particular experiments. They became two aspects of one electromagnetic system. A changing magnetic field could produce an electric field. A changing electric field could produce a magnetic field. The relationship could travel outward through space. In that possibility, Maxwell found waves. Not water waves, not sound waves moving through air. Electromagnetic waves, disturbances in electric and magnetic fields able to move across space. The idea was startling enough on its own, but then came the deeper surprise. When Maxwell calculated how fast such waves should travel, the speed matched the known speed of light. The implication was almost breathtaking. Light itself appeared to be an electromagnetic wave. The story that began with rubbed amber sparks, shocks, glass jars, frog legs, batteries, compass needles, and moving magnets had now reached sunlight, candlelight, starlight, and every visible thing. The glow by which the world was seen was not outside the electrical story. It belonged to it. This is the intellectual summit of the documentary. For centuries, electricity had seemed like a scattered set of strange behaviors. It pulled bits of straw. It stunned the hand. It flashed in storms. It twitched muscle. It flowed from chemical piles. It bent a compass needle. It appeared in a coil when a magnet moved. Each stage looked like a separate marvel until the connections slowly gathered. Maxwell's work gave the gathering a form. He did not make electricity simple. In some ways, he made it more mysterious. A spark and a beam of light were now relatives. A magnet and a changing electric field belonged to the same language. Empty space was no longer passive emptiness. It could carry electromagnetic waves across enormous distances. The invisible had become mathematical. Mathematics in this part of the story did not drain the wonder from electricity. It allowed the wonder to become exact. It gave scientists a way to say not only that electricity and magnetism were connected, but how they were connected. It allowed prediction. It allowed comparison. It allowed scattered evidence to become a structure future experiments could test. Observation gives the clue. Experiment tests the clue. Theory can reveal consequences no one has yet seen. Maxwell's equations did not merely organize the known past. They pointed forward. They implied that electromagnetic waves should exist beyond visible light waves that might be created, detected, and studied. For a time, that prediction waited. The waves existed in mathematics before they existed in the laboratory. This is another form of trial and error, quieter than the earlier ones. Instead of a jar that works before the theory is understood, here a theory reaches beyond available demonstration. It says, if the language is right, then nature should be able to do this. Science now had to ask whether the equations were only beautiful or true. That question led to Heinrich Hertz. In the 1880s, Hertz designed experiments to produce and detect electromagnetic waves. His apparatus did not look like the later radio world it would help make possible. There were no broadcasting towers, no household receivers, no voices crossing oceans for ordinary listeners. There were sparks, metal conductors, resonators, and careful arrangements in a laboratory. Once again, the future entered quietly. Imagine a room where a spark jumps across a small gap. Nearby, separate from the first circuit, another small gap answers with its own spark. There is no wire carrying the current directly between them. Something has traveled through the space between the apparatuses. A disturbance has left one circuit and been detected by another. This was not yet radio as daily life would know it, but the air had begun to behave like a pathway. Hertz generated rapidly oscillating electrical sparks and detected corresponding effects at a distance. A spark in one part of the room could produce a response in another, not through direct connection, but through waves traveling through space. The field disturbance predicted by Maxwell had become experimentally real. The mathematics had returned to the table. This was a beautiful reversal. Faraday's experiments inspired Maxwell's mathematics. Maxwell's mathematics predicted waves. Hertz's experiments brought those waves back into physical demonstration. The cycle was complete in a way that feels almost musical, hand to equation to wave back to instrument. Without static electricity, there would have been no early curiosity about charge. Without Leyden jars, no intensified sense of stored electrical force. Without Franklin and atmospheric electricity, no connection between small sparks and large natural events. Without Galvani and Volta, no continuous current. Without Ørsted, no bridge between current and magnetism. Without Faraday, no induction and no field imagination. Without Maxwell, no unified mathematical system. Without Hertz, no experimental confirmation of electromagnetic waves beyond light. The chain had become astonishingly long, and still it had not been straight. At every step, people had misunderstood something. They mistook visible parts of an apparatus for the source of electrical storage. They debated fluids and fires. They read frog muscle as a direct window into the electricity of life. They expected magnetism to produce electricity under the wrong conditions. They struggled to imagine influence through space. But each misunderstanding left behind a tool, an experiment, a correction, or a question. By the time Maxwell wrote his theory, the errors had not disappeared. They had been transformed into a more durable understanding. The wrong images had helped the mind climb toward a better one. Maxwell's achievement was not a sudden final answer descending from above. It was a synthesis. It gathered the labor of many generations. It gave mathematical form to the trial and error of experimenters who had been touching shocking rubbing wiring, rotating, and measuring the invisible for centuries. The equations were not a replacement for the messy room. They were what the messy room had slowly made possible. Electricity is not merely what flows through a wire. Magnetism is not merely what pulls iron or turns a compass. Light is not merely brightness. These are connected appearances of a deeper electromagnetic reality, one that can be stored, discharged, induced, radiated, reflected, refracted, and carried through space as waves. The ordinary world becomes less ordinary. A candle flame, a beam of sunlight, a radio wave, a current in a wire, a magnet near a coil, a spark in dry air, all belong to a family of phenomena that early observers could not possibly have held in one thought. The human story of electricity is in part the slow enlargement of what could be imagined together. Maxwell enlarged it almost beyond recognition, yet the enlargement did not immediately become everyday life. A theory of electromagnetic waves does not by itself build a radio network. A laboratory spark does not by itself electrify a city. A mathematical unification does not solve insulation generation distribution cost safety standards or engineering practice. Understanding had advanced, but the electric world still had to be built. Science can reveal a principle before society learns how to live with it. Faraday's induction gave the principle of generation, but building reliable generators required materials, design, labor, and industry. Maxwell's waves revealed a new form of transmission through space, but practical communication technologies required later inventors, engineers, systems, and institutions. The invisible fields had become a language. Now that language had to become infrastructure. Once electricity and magnetism were unified, the old scattered history looked different. The amber was no longer a curiosity alone. The spark from a jar was not a parlor trick alone. The storm was not heavenly fire alone. The twitching frog leg was not merely an anatomical oddity. The compass needle was not merely a disturbed instrument. Each had been a partial entrance into the same hidden order. The world had been teaching the lesson in fragments. Human beings had needed centuries to hear it. Electricity had not changed from age to age. It was always present in matter storms, nerves, magnets, light, and space. What changed was the human ability to connect its appearances. Nature was not silent. The evidence was everywhere. But it came in forms too different for the early mind to unify. By Maxwell's time, the map had become almost cosmic. Electricity was no longer only an experimental curiosity or a useful source of shocks and currents. It was part of the structure of light itself. It traveled through space. It linked physics, chemistry, technology, and perception. It connected what happened on a laboratory bench to what arrived from the sun and stars. Hertz's confirmation made that invisible reality harder to dismiss. His sparks showed that electromagnetic waves could be created by human apparatus. They could move across space and be detected. The field was not just an elegant idea. It had consequences one could see in the behavior of instruments. In a way, Hertz made Maxwell audible to the laboratory, even before the world learned to turn those waves into messages. The radio age was still ahead, but the door had opened. From this point onward, electricity was not merely something that could be generated and used. It was something that could carry information without a wire. It could travel outward as waves. It could cross rooms, landscapes, oceans, and eventually the spaces between planets. The same hidden structure that explained light would one day carry voices, music, images, and data through the air. For now, the point is not to rush into modern technology too quickly. The point is to feel the quiet grandeur of understanding. The centuries of shocks, sparks, mistakes, and small deflections have reached a moment where the invisible has been given a language strong enough to predict what no one had yet built. Not the power to light a city yet, but the power to know what might be possible. As this section closes, imagine the electric story held in two images. In one, Faraday stands among coils, magnets, and needles, watching a small instrument move when a magnetic condition changes. In the other, Maxwell sits with symbols, turning those physical intuitions into a pattern that says fields can travel as waves and that light belongs to the same family. Between them lies one of the great passages in scientific history. Experiment becomes theory. Theory becomes prediction. Prediction becomes experiment again. From that cycle, the electric world begins to approach its final transformation. The invisible force has been named, stored, shocked, drawn from storms argued over in flesh, made continuous in batteries linked to magnetism, generated by motion, and written into the language of fields and waves. What remains is no longer only to understand it. What remains is to build with it, to send it through streets and walls, to make it useful, safe, stable, profitable, contested, and ordinary. The equations have opened the way. Now the city waits in the dark. The city waits in the dark. For most of human history, night belonged to flame. A lamp, a candle, a hearth, a torch in the street. Each made only a small island of light against a much larger darkness. Light had to be fed. It smoked, flickered, consumed oil, wax, wood, or gas. It warmed the air around it and carried danger with it, because every flame was also a small possibility of fire. Then electricity began to enter the city. At first, it did not arrive as a finished system. It did not quietly spread through walls safely hidden behind switches and standards. It came through experiments, demonstrations, competing designs, failed lamps, unreliable generators, dangerous wires, fires, shocks, business rivalries, and public uncertainty. The science of electricity had advanced enormously, but the practical electric world still had to be built one problem at a time. Maxwell had given electricity and magnetism a language of fields and waves. Faraday had shown that motion and magnetism could generate current. Hertz had brought electromagnetic waves back into the laboratory. But understanding a principle is not the same as building a civilization around it. A city is not a laboratory bench. It is crowded, wet, dirty, expensive, political, and alive. It has streets, homes, factories, theaters, hospitals, underground pipes, wooden buildings, metal structures, frightened citizens, impatient investors, and workers who must install systems that cannot fail too often. To bring electricity into such a place, people needed more than discovery. They needed engineering. And engineering is trial and error with consequences. Electric light became one of the most visible promises of this new world. The desire was simple light without flame. But the path was not simple. Early arc lights could be brilliantly bright, useful for streets or large spaces, but often harsh and difficult to control for ordinary rooms. Incandescent lighting, the gentler glow from a heated filament inside a bulb, required a different kind of patience. The problem was not only to make something glow. The problem was to make it glow long enough, safely enough, cheaply enough, and reliably enough to matter. Many materials could become hot and luminous when current passed through them, but they might burn out too quickly. The bulb needed a vacuum or controlled atmosphere. The filament needed the right material. The circuit needed the right resistance. The system needed generators, wiring, switches, meters, and maintenance. A lamp was never only a lamp. It was the visible tip of an entire hidden network. Inventors and engineers tested materials, shapes, voltages, distribution systems, and business models. Joseph Swan in Britain and Thomas Edison in the United States both worked toward practical, incandescent lighting. Edison's achievement was not simply a bulb, but a system generation distribution sockets, meters, switches, and a practical vision of electric service. The light in the room depended on the machinery behind the wall. A person could press a switch and see light appear, but behind that gesture stood coal steam dynamos, copper insulation, labor investment, and regulation. Electricity became ordinary only by hiding most of its complexity from the person using it. In the early years, that complexity was not well hidden. Wires crossed streets. Installations varied in quality. Standards were not yet settled. Some systems were dangerous. Fires and accidents forced engineers to rethink insulation fuses, grounding spacing, and protection. The public had to learn what electricity could do and also what it could do wrong. Electricity was no longer only a scientific mystery. It had become a public risk. The new electric systems entered a world already using other forms of energy and lighting. Gas lighting existed in many cities. Steam power drove factories. Telegraph wires had already crossed landscapes and streets. Electric lighting and electric power did not appear on an empty stage. They had to compete with older systems, fit into existing cities, and persuade people that the new danger was worth the new convenience. The invisible force now had social consequences. It changed labor. It changed streets after sunset. It changed factories, transportation, communication, domestic life, and eventually sleep itself, because artificial light altered the boundary between day and night. But none of that happened cleanly. Every expansion created new questions. How far could current be sent? At what voltage? With what losses? Through what kind of wires? Who would own the system? Who would regulate it? What counted as safe? The electric world had to become standardized before it could become trusted. One of the great practical debates concerned direct current and alternating current. Direct current flows in one direction. Alternating current reverses direction periodically. In the early years of electrification, this was not merely an abstract technical difference. It shaped how power could be generated, transmitted, transformed, sold, and used. Direct current systems were important in early urban lighting, especially in local networks. But sending power over longer distances created serious challenges. Alternating current, especially when paired with transformers, allowed voltages to be raised for transmission and lowered again for safer use. This made larger power networks more practical. The debate became technical, commercial, and public. Names like Edison, Tesla, and Westinghouse often dominate popular memory, sometimes so strongly that the larger history is flattened into a drama of heroes and rivals. But the deeper point is not simply who won. The deeper point is that even after electricity had been scientifically understood in powerful ways, society still had to discover which electrical systems could serve cities, industries, and homes. The answer emerged through experiments, failures, demonstrations, accidents, lawsuits, propaganda, and engineering performance. The current wars were not only about personality, they were about infrastructure under uncertainty. People were deciding what kind of invisible force would run through public space. They were deciding how much danger was acceptable, how efficiency should be balanced against safety, and how a technology should be made trustworthy at scale. This was a different kind of experiment from Faraday's coil. The apparatus was now the city. Failures became harder to contain. A bad filament could burn out in a lab. A poor urban installation could start a fire. A badly managed wire could kill a worker or passerby. A power station failure could darken a district. As electricity moved outward, trial and error became more expensive, more political, and more morally serious. This did not stop electrification. It made it more disciplined. Engineers learned to insulate better, interrupt dangerous currents, design safer switches, improve lamps, protect circuits, regulate voltage, and build systems that could be maintained. Standards developed because variation was dangerous. A world of private experiments had to become a world of shared rules. This is one of the least glamorous but most important parts of the electric story. Civilization does not run on discovery alone. It runs on repeatability, maintenance, compatibility, and trust. A wire must behave as expected. A plug must fit. A lamp must not demand expert attention every night. A generator must supply power at a usable frequency and voltage. A worker must know what is dangerous before touching a line. Electricity became modern when it became reliable enough to be boring. That boredom was an achievement. The same force that once stunned spectators from a Leyden jar could now be routed quietly through walls. The same family of phenomena that bent a compass needle could run motors in factories. The same principles of induction that Faraday saw in small apparatus could operate dynamos and transformers. The same electromagnetic world that Maxwell described could later carry signals through the air. The invisible had become domesticated, but never fully harmless. Even in the modern home, electricity remains powerful. It is simply surrounded by layers of design that protect us from noticing its danger. Insulation breakers, grounding codes, and careful engineering stand between the user and the force. The ordinary switch is possible because so much trial and error has been absorbed into the system. That is why the finals image of the electric world should not be only bright, it should also be hidden. Behind the calm glow of a lamp is a history of mistakes corrected. Behind a quiet outlet is a history of shocks, fires, melted wires, bad assumptions, and better standards. Behind a city skyline at night is the slow accumulation of scientific theory, engineering practice, industrial labor, and public learning. Electricity looks effortless because so much effort has disappeared into the walls. Communication followed a similar path. The electric telegraph used current to send signals over long distances, turning electricity into a carrier of information. Later electromagnetic waves opened the way to wireless communication. Radio would make the air itself seem newly alive with messages. But once again, the practical systems required more than the discovery of a principle. Signals had to be generated, controlled, detected, amplified, tuned, separated from noise, and made useful. The trial and error continued now in the realm of information. A wire could carry a pulse, but codes had to be invented. A wave could travel through space, but transmitters and receivers had to be built. Interference had to be managed. Frequencies had to be organized. Devices had to become stable, affordable, and understandable. The electric world did not arrive all at once. It spread in layers. First there were sparks and shocks, then jars and lightning rods, then batteries and currents, then electromagnets, motors, generators, lamps, wires, transformers, power stations, telegraphs, telephones, radios, and countless devices that turned electrical principles into daily habits. Each layer made the previous one seem more ordinary, but each had its own mistakes. The modern person enters this story late. We live after the shock has been softened into convenience. A phone charges while we sleep. A refrigerator hums through the night. A traffic signal changes color. A hospital monitors a heartbeat. A train moves through a city. A message crosses the world in less than a second. The force that once had no name has become the background of ordinary time, and yet the deep history remains inside it. The lamp remembers the filament problem. The grid remembers the current wars. The motor remembers Ørsted and Faraday. The transformer remembers induction. The radio remembers Maxwell and Hertz. The battery remembers Galvani's frog and Volta's pile. The lightning rod remembers Franklin Dalibard Richman and the dangerous attempt to bring the storm into experiment. The whole electric world is layered with old uncertainty. Early trial and error asked what electricity was. Later, trial and error asked how electricity could be stored, guided, generated, transmitted, priced, regulated, standardized, and made safe enough for ordinary life. The question moved from nature to civilization. At first, human beings were trying to understand a force. Later, they were trying to build a world around it without being destroyed by their own partial knowledge. That is why the history of electricity is not only a history of ideas and not only a history of inventions. It is a history of learning how to live with invisible power. That learning is still unfinished. Modern grids face new forms of trial and error, renewable energy integration, storage demand, resilience, extreme weather, and the challenge of building systems that remain stable in a changing world. The details are modern, but the pattern is old. Electricity still requires humility. It still rewards careful design. It still punishes careless assumptions. The electric world remains a system we must constantly maintain. This gives the story a quiet circularity. We began with people watching strange effects they did not yet understand. We end with people living inside vast electrical systems they often do not notice. The mystery has not vanished completely. It has become embedded in infrastructure. We no longer gather in a room to feel the shock from a jar. But we live inside the jar's distant descendant. A city at night is a kind of enormous electrical apparatus. Current moves through copper and aluminum. Transformers hum. Switches open and close. Generators respond to demand. Signals pass through wires and air. Light spills from windows. Elevators rise. Screens glow. Machines breathe quietly in the walls. Most of this happens beyond attention. That hiddenness is the mark of success, but it can also make us forget the long struggle that made it possible. Electricity feels natural now because the systems around it are mature. But it is not natural in the sense of being effortless. It is natural only because generations of experimenters, scientists, engineers, workers, and users slowly taught it how to enter human life. Or perhaps more accurately, they taught human life how to receive it. Electricity was always present in the world, in storms, bodies matter, magnetism, and light. It did not become powerful because humans invented it. It became useful because humans learned to ask better questions of it, and because they were willing to correct themselves when the answers did not fit. The wrong ideas mattered. The jar as a bottle of electrical fluid. The frog leg as proof of a simple animal electricity. The expectation that a still magnet should produce current. The assumption that a working lamp was merely a glowing object rather than a whole system. Each misunderstanding shaped the next attempt. Each attempt left behind an instrument, a warning, or a principle. The electric world was built from corrected errors. As the section closes, imagine the city again. Not in the harsh brightness of noon, but at night, when its electrical nature becomes visible. Windows shine in tall buildings. Streetlights line the roads. Trains move under the ground. Signals blink on towers. Somewhere in rooms too ordinary to notice people read. Work, rest, cook, listen, speak, and sleep under the quiet service of a force that once lived only as mystery. The glow is calm now, but beneath it is a long history of sparks, shocks, storms, twitching muscles, turning needles, moving magnets, invisible fields, and dangerous wires. Beneath it is the patience of many generations, learning that nature does not give its secrets cleanly. It gives effects, first explanations later, and safe systems only after still more effort. Electricity became ordinary because human beings kept returning to what they had misunderstood. They touched the shock, watched the spark, followed the current, traced the field, corrected the machine, rewired the city, and tried again. And because they did, the night itself slowly changed. By the end of this journey, electricity no longer feels like something that simply arrived in the modern world. It feels older, stranger, and more patient than that. It was present long before wires crossed streets, before lamps filled rooms, before signals moved through the air. It waited in small shocks, storm clouds twitching muscle magnetic needles and the quiet space around charged objects. What changed was not electricity itself, but the human ability to follow it. People misunderstood it, named it poorly, trapped it in jars, argued over it, feared it, displayed it, measured it, and slowly learned from the ways their explanations failed. Each mistake narrowed the mystery a little. Each failed idea left behind a better experiment. Each experiment made the invisible world slightly less unreachable. Science does not always move forward because someone sees the truth clearly at once. Often it moves because someone notices that an explanation is not enough. A spark behaves strangely. A needle turns. A current appears only when a magnet moves. A theory becomes mathematics, and then a small spark in another room proves that the waves were real. Electricity became ordinary only after many generations made peace with how mysterious it was. The light above a desk, the hum inside a wall, the phone charging beside a bed, the distant city glowing after sunset, all of these rest on centuries of uncertainty, danger, patience, correction, and care. So, when we look at the electric world now, perhaps we can see more than convenience. We can see the jar on the table, the kite beneath the storm, the frog leg on the bench, the compass needle turning the magnet moving through the coil, the equation becoming a wave, and the city slowly learning how to shine. It is a long human conversation with an invisible force, carried through error, curiosity, and persistence, until the night itself could be gently lit.